Hi, my name is Mahdieh Kamalian. The focus of my PhD project is on fog transport mode detection system, which intends to detect the modes of users such as car, bus, subway, and etc. The information related to transport mode choices of individuals have been used in different areas and mainly for event planning and design. Such travel information becomes even more important for traffic management when a fast response is required for the allocation of one specific mode. For example, a football match may change the regular public transportation demands. Another use case is entertainment. It can suggest the users the entertainment facilities when they are reaching to a nearby bus station. Also, it can be used for health and epidemiology. For example, during a pandemic or for detecting abnormal activities of patients with Alzheimer or any other mental pathologies to protect them from danger. Most TMD systems rely on machine learning algorithms which follow four steps: data collection, pre-processing, feature extraction, and classification with a previous training phase. And sometimes there is a post-processing step. Based on the steps done on the smartphones or remote servers, we can categorize TMD approaches to local or remote. In a remote approach, data collection is done on a smartphone and the collected data is sent to a server for pre-processing, feature extraction, and classification. However, in a local approach, all of these four steps are done on the smartphone. The training phase, although, can still be done on a server or on the smartphone itself. Our objective is to develop a smartphone application and the corresponding fog architecture for a local TMD system. To achieve our objectives, we have four main requirements: high accuracy, which depends on all TMD steps and mainly the ML algorithm; low latency, which is implicitly omitted when we perform local classification; low battery consumption, which is mostly dependent to data collection step; and finally, generalization, which accounts for a system that its accuracy is not significantly affected by different parameters such as the smartphone position, user variation, or different geographical locations. What are the challenges? We intend to integrate our application with another TMD application called DW’20. The integration of these two apps is the first challenge. Another challenge is the delay because we intend to provide a real-time TMD app. Accuracy is the most important one, especially when it comes to differentiation of different motorized modes. Battery consumption, which is mainly dependent to sensors we use, such as GPS. And finally, introduction of a generalizable system. Previous studies proposed different local solutions. Some of them propose single accelerometer solutions. Some other studies are considering all motorized modes or rail modes as a single group. Others, even with fine-grained motorized modes, could not achieve high accuracy. And finally, most of existing local studies fail to meet all the TMD requirements as shown in the table. Our solution respects all TMD requirements. We intend to integrate our application with another application called DW’20. To improve the accuracy of DW’20, we use a random forest classifier trained with data collected by the GPS and the accelerometer sensors. Then a post-phase correction takes advantage of the magnetometer and the complementary information such as maps and timetables of public transports provided by the fog servers in each city. To minimize latency, we perform classification locally on the smartphone, while training and storing TMD results are done on some closer servers to the edge, such as fog servers. To limit the battery consumption, GPS sensing is done with a low frequency, and we fulfill the gap by the detailed information of public transportations. To meet generalization requirements, our TMD system is trained on a large dataset collected by different users from different locations with no preferences for their smartphone position. So our proposed architecture consists of three layers of edge, fog, and cloud. We perform classification on the edge layer, training and storing data on fog layer, and long-term analysis on the cloud layer. In conclusion, our solution is a fog local TMD which is able to meet all the TMD requirements. We also plan to introduce a peer-to-peer smartphone architecture as our future work. In this approach, we connect nearby smartphones to other smartphones, which are the most experienced ones in a city or have the best sensors. Thank you for your attention.